Hello and welcome back to my channel and to my series of videos on making a tool post milling spindle for my lathe. The motor I want to use for driving the spindle is this 48 volt 300 watt motor. For power transmission I want to use a belt drive, either a PJ belt drive or a PU round belt drive. Later in the video we will also take a look at how I am planning to mount the motor to the spindle. One thing right from the start. The motor of my lathe died while working on the mount, so we won't get to milling a thread in this video. I also received two thread milling cutters, one for 60-degree threads and one for 55-degree threads. We will also take a detailed look at these later in the video. But right now I need to address the audio quality of the voiceover. In the last video I was pressed for time and I was using a DJI Mic 2 handheld to record the audio. Going forward I want to use a proper microphone for recording the voiceover. To mount the microphone I'm using a Manfrotto 396B3 articulating arm, the one you can see me fiddling around here right now. As so many things from Manfrotto, it's a pretty great product, but has also some annoying flaws. It comes with a camera bracket that mounts to this spigot here. The camera bracket itself is pretty great, but the way it's mounted to this spigot sucks. If you loosen the screw to rotate the bracket, the whole thing comes loose. As you can see, this design isn't really thought through. So I have to do something about it. Namely making a better fitting spigot that fits my needs. Let's start with disassembling the arm and see what we've got here. Okay, so the spigot is held in one of the joints of the arm, and I need to disassemble this joint to get the spigot out, and that's what I have to replace then. This is a 10mm nut. So I'm unscrewing it, and so the joint is made from 4 plastic parts that are held together with a screw and some additional hardware. 2 parts hold the spigot and 2 parts clamp the 2 rails of the arm. Okay, so when you turn this lever a quarter of a turn, you tighten it. You can see there is a ramp, and these 2 pegs on the lever are right on this ramp, and this is what locks a joint. So this spigot has a small shaft running through it, and this shaft locks into the hole I'm pointing here. And there is another hole on the mating other half, and this prevents the spigot from rotating or coming loose when the joint is not tightened. So I need to replicate this in the spigot I am building. So let's start with taking some measurements. This small shaft has a diameter of 4mm and a length of 18mm. It is 22mm from the end of the spigot. And the whole thing has a diameter of 44mm, so it's right in the middle. The whole thing is 70mm long. The part that gets clamped in the joint has a diameter of 13 millimeters, and the thing that goes into the bracket a little bit under 16.5 millimeters. And this here measuring the inside diameter, a little bit larger of course, and it is also 22 millimeters deep. So let's get to machining. We start with 18 millimeter round stock of mystery steel, good enough for this application. First facing it off and then marking the length of 70 millimeters. I'm setting a stop here to know for how long I have to turn the stock down. Okay, so let's fast forward this a little bit. Yeah, it doesn't look that good, but there's enough material that has to come off. So let's take a measurement. Yeah, still plenty of material that needs to come off. And thanks to the magic of video editing, we have already hit our target dimension of 13 millimeters. Let's do a test fit in the clamp. Looks good to me. Now let's check with the spigot in the other hole, if we have it straight. Yeah, looks good. Next step is cleaning the surface up a little bit with some sandpaper. This side is now finished, so I now need to turn the part around and start machining the other end. This is the side that goes into the camera bracket. And now you can see me trying my hand at being a pantomime. I'm sorry. Just a quick measurement to confirm the diameter again. Yeah, still 18 millimeter. Okay, let's starting to machine this side. We need to turn it down to around 16.5 millimeters and a length of 22 millimeter. I once again start with a facing cut. After that there come some horrible noises, and once I'm deciding on what I'm going to do, I start with turning the part down. I am changing to a ground aluminium insert to get a better surface finish on the finishing pass. It goes on okay, but I want to remove a little bit more. I am marking the spigot by pushing into the material with the screws, and I'm going to relieve the material here a little bit. With that, any burr caused by the screw pushing into the material won't get the bracket stuck, and also it prevents the bracket from falling off when the screw is only a little bit loose. You have to back it out 1 or 2 turns to remove the bracket. The next step is drilling the cross hole. I didn't find my 4mm reamer, so I'm finishing just with a 4mm drill, and I will be sizing the pin that goes into that hole accordingly. Now on to making the cross pin. For material, I'm using a shaft that I harvested from an old printer. This material turns pretty well, so I'm just using the finishing insert here. I'm fitting that cross pin by feel. I want a little bit of interference fit so that it doesn't fall out on its own. I'm using a hacksaw to cut it off, and then I'm going to flip it around. I'm facing it off so that I can measure its length in the next step. We need a length of 18 millimeters, so 4 millimeter need to go. Good enough. I forgot that my hands aren't see-through, so you have to deal with this shot here. I estimated correctly and the cross pin can be pressed in easily. The cross pin is 5 millimeters longer than the diameter of the spigot, so I'm going to use 2.5 millimeter drill bits as spacers to have it in the middle. As you can see, I made a second part and I will be using that one to cap off the hole in the joint. So now on to reassembling the arm. The fit is good and just what I wanted. Now adding the blanking spigot and the real spigot. I guess strictly the blanking one isn't necessary, but why not? Now screwing everything together. And now I'm setting the tension so that's not too loose and not too tight. And now on to using that thing. It has a little bit of play, but it feels just right. Now adding the microphone. I'm using a pop screen, and this pop screen was mounted using this clamp here. That was also very impractical. So I made another plug and threaded it to mount the pop screen into the second hole on the bracket. I think now it's a pretty good setup for recording audio. And now let's take a close look at the thread milling cutters I got. This is a 55-degree thread mill and this is a 60-degree thread mill. This one is tiny. When I bought this, I wasn't sure on the size, so I just got a 1 millimeter one and I could easily have gone with a larger one. We will be using my toolmaker's microscope to take a look at the thread profile, and for holding the milling cutters I whipped out this fixture here. The thread mill gets clamped and now we can take a look under the microscope. just to explain the setup and my way of thinking here. In the insert shot, you see a view through the eyepiece of them. Now I'm going to align one of the flanks of the thread milling cutter with one of the lines of the crosshair. And then I'm going to read the scale on the rotating stage. Here we are at 100.6 degrees of angle. I'm going to note that, and now I am rotating the stage so that the second flank of the thread milling cutter is aligned with the same crosshair line. Okay, so now the second flank of the milling cutter is aligned, and now I can take a second reading, and we get 161.6 degrees of angle. When I subtract the other measurement, we get a measured angle of 61 degrees. So for me, that's close enough to 60 degree. Now let's do the same thing for the 55 degree thread mill. I think I'm overdoing it a little bit here, but now it's good enough. And we take a first reading. It's 89.2 degrees. So let's note that down and rotate the stage so that we can take a second reading. So our second reading is 144.2 degrees. And when I subtract the first measurements, we get exactly 55 degrees. So perfect measurement. Now let's take a look at the Tool Post Milling Spindle and the motor I'm going to use to power the spindle. So in the bottom you see the clamp we made in the last video, then the spindle, and on top is the motor. And I've already made a second clamp, and I'm going to use this clamp on the spindle to mount the motor to the spindle. The clamp is going to mount on the back side of the spindle, and I'm using that hole and this shaft here to make a pivot to be able to tension the belt correctly. This is a plate that's holding the motor and also the other end of this shaft here. It's screwed on with four screws, and then you can see this threads into here and that goes into that clamp, and I still need to come up with a way to tension the belt. I got this 4 PJ belt and 2 pulleys to drive it. I think it's a little bit overkill for this application, but we're going to see if it works, or maybe if I'm switching to PU round belts. I think these would be also good enough. Since the shaft is without any recesses, I added a lead ball into the into the thread here, so that the surface of the shaft doesn't get distorted when mounting the pulley. So, and this would be the other option. It's a PU belt, and it just gets welded. To be able to read out the RPM of the spindle, I got this gauge here. It has an optical interrupter, and I 3D printed this tacho wheel here, and it gets clamped also onto the shaft of the spindle. And with that, it's time to say goodbye. Or is it? Unfortunately, the motor of my lathe died right after recording this clip. So, thank you all for watching, and goodbye.